It is essential to look at the chemistry of life when studying anatomy. Why? Chemistry is basically the study of matter and the changes it undergoes. Matter, by definition, is anything that has mass and takes up space. The human body has mass and it takes up space, and therefore we are classified as being made up of matter. The interactions of chemical compounds in our bodies make us who we are. Therefore, it is important to understand how the human body functions. Matter is composed of tiny particles called atoms. Therefore, the smallest form of matter is an atom. There are approximately 109 different types of atoms. A substance made up of one specific type of atom is referred to as an element. Now we're going to look at the atomic structure. What makes up an atom? An atom is composed of smaller subatomic particles, and these would include the protons, which are positively charged, neutrons, which are neutral. Both protons and neutrons are found in the center of the atom in a region referred to as the nucleus, and here you see the nucleus. And then the third subatomic particle would be the electron, which is negatively charged. The electrons are found in energy levels all around the nucleus of an atom at a specific distance from the nucleus depending on their energy. That's why they're referred to as energy level. Now, each element has a different number of proton in its nucleus. So what identifies an element is basically the number of protons in its nucleus, and that is referred to as the atomic number. The atomic number is the number of protons, positively charged particle in the nucleus of an atom. In a neutral atom, the number of protons will be equal to the number of electrons. So if lithium, for example, has atomic number 3, that means it has 3 protons, and if it's a neutral atom, it will have 3 electrons. Another term we often use in chemistry is the mass number. The mass number is equal to the number of protons plus the number of neutrons in the nucleus of an atom. The mass number is always a whole number. This should not be confused with the atomic weight. The atomic weight is the average of all known isotopes of that element. Later on we'll talk about what isotopes are. But the atomic weight has decimals. The mass number does not. It is a whole number. When we enlarge the periodic table, you will notice the different elements and how they are annotated on the periodic table. For example, if we take a look at cobalt. Cobalt, here, notice that the symbol is the first letter of the name capitalized and second letter lowercase. You will see the same for nickel. However, there are certain elements, for example, iron, that it does not begin with the first letter or the first and second letter, but that's because those elements, and there are 11 of those, are named based on their Latin name. Iron would have been ferric or ferrous, copper, cupric or cupris. So that's the reason why they're not named, their symbols are not the first and second letter of their names. Now, when looking at the periodic table, we also see certain numbers. For example, if we look at cobalt, you have 27. 27 is your atomic number. And then the lower number, notice is 58.9333195. That is the atomic weight. Notice the difference, which I mentioned before. The atomic weight has decimal. If I say that the atomic mass of cobalt is 59, that's I give you the atomic mass. as being 59. I could ask you how many protons are in cobalt, how many electrons in cobalt, and how many neutrons in cobalt. Now, the number of protons and electron is the same because the number of proton is the atomic number, 27, and the number of protons will be equal to the number of electrons, therefore electrons would be 27. As far as the number of neutrons, we know that the mass number is equal to the number of protons plus the number of neutrons. If I say that the mass number is 59, and I know that the number of protons is 27, I can figure out the number of neutrons. Therefore, 59 minus 27 is equal to 32. The number of neutrons would be equal to 32. So you can see that we can gain a lot of information from the periodic table. And again, we need to notice that the difference between mass number and atomic weight is that the mass number has to be a whole number because it's the sum of the number of protons and the number of neutrons. Now, the atomic weight is the average of all the known isotopes. Therefore, let's go on to define what is an isotope. An isotope is atoms of the same element containing the same number of protons but different number of neutrons. An example of this would be the hydrogen atom. You have hydrogen 1, hydrogen 2, and hydrogen 3. Deuterium is hydrogen 2, tritium is hydrogen 3. If you notice, they have the same number of protons, meaning one proton in the nucleus, but they have different number of neutrons. Hydrogen 1 does not have any neutrons. Hydrogen 2 has one neutron, and hydrogen 3 has 2 neutrons, but they all contain one proton. Many isotopes have radioactive nuclei, which means that they begin to disintegrate and give off radiation. That is the reason why we use carbon-14 dating in order to determine how much of this radioactive isotope remains and thereby identify the age of the fossil. It is also used in minute amounts in radio imaging, such as PET scans. They are used to tag molecules throughout the body and identify different illnesses. However, radioisotopes do release gamma rays, and they release alpha and beta that can destroy the cell. Electrons play a very important role in bond formation. Atoms will form bonds with each other in order to obtain a valence electron within their outermost energy level. This is referred to as the octet rule. If you remember, back in chemistry, you were told that electrons within an atom will be lost or shared in order to form a bond. For example, here we have hydrogen. Hydrogen has one electron at its outermost energy level, but it wants to gain 2 electrons. So it's going to take an electron from another atom. On this side we see carbon. Carbon has a maximum of 8 valence electrons, but it only has 4, so it needs to gain 4 more. And here we see sodium. Sodium has one outermost energy level, but if you see on the inner side, it has 8. So if we could get rid of that one, it would be fantastic for sodium. In other words, these atoms are either going to gain, lose, or share electron in order to have the octet rule of 8. Here we see a clear example of a reaction occurring in which the electrons are being donated and accepted by the different elements. For example, sodium here. Sodium has 11 protons, 11 electrons. The way it distributes its electron, it will have 2 electron in the first energy level. It will have 8 electron in the second energy level, making it 10, and then it has one extra electron in the outermost energy level. But all elements are going to react in order to have 8 in the outermost energy level, which is referred to as valence electron. Now, sodium really wants to get rid of that one electron. If it gets rid of that one electron, it ends up with 8 on the inner side. So what happened? It sees an atom of chlorine. Chlorine, if you notice, will have 2 in the first energy level, 8 in the second energy level, and it has 7 in its outermost energy level. It needs 1. So sodium is being a good neighbor, and it's going to give that 1 electron to chlorine, and this is going to form a bond where sodium will now have a positive charge because it lost an electron, so it has more protons than it has electron, and chlorine will carry a negative charge because now chlorine has an extra electron. Sodium is said to be a cation. Cations have positive charge. Chlorine is referred to as an anion, meaning it has a negative charge. Now, in order to remember this, cations, positive, anions, negative. Remember the T for cation, the N for anion. N stands for negative, T stands for positive. And this is referred to as an ionic bond, where electrons are being transferred. There are also covalent bonds in which the electrons are being shared. An example of this would be between two hydrogen atoms. If you notice, hydrogen here has 1 electron. This other hydrogen has 1 electron. Both of them want to have 2, so neither one of them wants to donate. So what happens is they are sharing their electron. They are sharing their electron equally, so this is called a non-polar covalent bond. Now, on this second picture, you can see a molecule of oxygen. Again, you have 6 valence electron on one, 6 valence electron on the other. In order to have 8, they both need 2, so they're going to share for them here. This is a double covalent bond. In this case, we see methane. Here's carbon. It has 4 valence electron. It would really like to have 8, so it's going to bind with 1, 2, 3, 4 hydrogens that only need 2 because they follow the duet rule, and forms methane gas, and this is also a non-polar covalent bond. Compounds are formed when 2 or more elements are bonded together. They may be in the form of ionic bonds, in which there is a transfer of electrons. Electrons are donated and they are accepted by the other atom, or they may be covalent bonds, and under covalent bond they're being shared together. Electrons are being shared. These electrons may be shared equally, meaning it is a non-polar covalent molecule, or they may be unequal sharing of electron, which is a polar covalent molecule. An example of this would be the water molecule. When we look at the water molecule, you can see a partial positive N, that is the hydrogen, and you can see the partial negative N, that is the oxygen. The oxygen, being stronger, is going to pull some of the electrons away from the hydrogen. That's why it is an unequal sharing of electrons. Therefore, it is a polar molecule. You will see the partial positive N being slightly attracted to the partial negative N of the neighboring molecule, and therefore forming a slight attraction. This is called hydrogen bonding. This is the reason why sometimes you see the water droplets that kind of attract each other, because there is hydrogen bonding. This is very important, especially when we talk about metabolism. Water is one of the most important molecules in the human body.